All right, this is Unit 8, the FRQ Part A. There is one question here, and it is a calculator active question. So if we look, it says Diego runs back and forth along a straight track during the time interval from 0 to 30 seconds. His velocity is given by this function. So remember, I'm not gonna put the entire thing on here because I am operating under the assumption that you've got it in front of you as well. So this is our velocity function. Part A says, what is the first time, T1, that Diego changes direction? So a change in direction means that your velocity is equal to 0 and that it switches signs. Or I guess specifically we should say the change in direction means that velocity switches signs, which means we're looking for where the velocity is equal to 0. Okay, so we want to write down what we're trying to solve. We are setting velocity equal to 0. This is a calculator active question. So what I'm going to do is I'm going to take this equation and graph it. You really want to double check that you are in radian mode whenever you're dealing with something that has trig. So I am just waiting for my calculator to load here. I'm hoping it has battery life. And so we'll plug it into our graph, and then setting it equal to 0 means you are looking for the x-intercepts. So we can find those once this thing decides it's going to load. Come on. Oh my goodness. There we go. All right, so new document. We are going to add a graph. Oh, for goodness sake. Here we go. Whatever we have here, we're just going to add a graph. So in the numerator, we want to make sure we have parentheses here. We're going to do 200 times the sine of, and then we use an x whenever we're graphing, no matter what the variable is. So x squared over 75. Close the inside of the sine function, close the numerator, divided by, and then parentheses for the denominator, x plus 1. All right, so we graph that. We'll see if this window works for us. So this right here is a t equals 0. And they go all the way from 0 to 30. So my window right now is only going up to 10. So if you're working with an Inspire, over on the menu here, there is a menu that we can change the window to whatever we want. So I always just like to do window settings. So we're just going to change it to 0 to 30, just like the problem has set up. And now let's graph again. So this right here, it says, when is the first time it changes direction? It changes here and here and here. So we want to look for this point right here. So on the Inspire, we're going to press the menu key, this menu to analyze the graph, and then we're looking for the 0, which is our x-intercepts. We set a lower bound, we set an upper bound, and then it basically catches our point in the middle here. So because this is the middle of our problem, 3 decimal places is not enough because we want to make sure that the end of our problem is accurate to 3 decimal places. So anytime in the middle, we want like 5 or 6 decimal places. So 15.3499, let's say 01. Why not? Okay, so that is the first time it changes direction. That's the first part of the question. Then it says find Diego's average velocity over the time interval from 0 to that time. So average velocity, or average anything, is this formula right here. So when you are asked for the average of f of x on a time interval, or not a time interval, but just any interval, you use this formula right here. So they said to use the average velocity, so we do 1 over 15.349901 minus 0, and then the integral from 0 to this value right here. And when you're looking for the average velocity, what you put in the integrand is the velocity function. So we set this up on the AP test. Because this is on a calculator section, all you have to do is write the setup equals, and then you let your calculator do the work. All right, so if we are in just a regular calculator page here, we put our little fraction out front. I'm going to put it in parentheses, times, and then we set up our integral. So menu, calculus, numerical integral from 0 to this lovely point right here. And then our integrand is just the velocity function. So we're going to set up a fraction, or you can put it in parentheses, whichever works for you. And then here we can do it in terms of t, just because you have the option to do whatever variable you want, or you can just keep it in terms of x if you're more comfortable there. So final answer needs to be accurate to 3 decimal places. So 10.504 if you're rounding, 3 if you're truncating. Okay, and it says his velocity in feet per second. So this would be in feet per second. Always make sure if there's a unit that you can use, that you are using that unit. All right, so that's letter A. Letter B. At time t equals 30, how far is Diego from his position at t equals 0? Notice they don't tell us what that position is, which is fine. We don't need to know it. We just need to know his displacement, which is how far he moved. So your displacement is always the integral of velocity. This is not officially material that you will see on this test, but it's part of this problem, so it's a great thing to recap for the AP test for anything that's coming up. So when you integrate velocity from time 1 to time 2, that is going to give you the displacement. It will tell you how much the position changed from 0 to 30, which is all they're asking for. We don't need to know where it ended up. We just want to know how much it changed. And this is a calculator question, so all you have to do is write this setup, and then you can plug it right in. So integral from 0 to 30 of our velocity function. All right, and that is 128.323, and that would be in feet. Because the velocity is given in feet per second, this gives us the change in position. When you integrate velocity, you get displacement. The antiderivative of velocity gives you position. So this would be a number of feet, how much he moved during those 30 seconds. All right, that's part B. Part C says find the total distance that he runs during those 30 seconds. So the difference between displacement and total distance traveled is that for total distance, you put absolute values around the velocity. So for total distance, you're integrating speed because you don't care if something is moving in a forward or a backwards direction. You just want to know how far they went. And so that involves throwing absolute values around. This gives you displacement. This gives you total distance traveled. So you will see that there's a big difference there. So I'm going to see if I can just add them in here. It might not work. I feel like it's not going to. I'm going to forget it. All right, let's try again. 0 to 30. Okay, so absolute values. Then we put the fraction on the inside. Notice the absolute values is only in the integrands. It is not around the entire, like it's not all around the outside here. It's just on the function on the inside. And it is very important that it's placed properly, because otherwise all it's going to do is give you the absolute value of this number, which would still just be the same as what we had up here. It's the function that you need to take the absolute value of. So there we go, we get 243. So that means that his direction was changing as he was going. This is how much he moved from beginning to end, like how different his position was. This is how far he actually traveled. So 243.425. All right, and one final part for this problem. It says let A represent his acceleration. Using correct units, explain the meaning of this integral right here in the context of the problem. So this, when you integrate velocity, you get the change in position. So if you apply that logic one step further, when you integrate acceleration, you get the change in velocity. So this is the, we'll even throw in net change. Net change works. And this is using correct units, so net change in velocity in feet per second. From 5 seconds to 10 seconds. So that's what it's giving us. Let's actually find that number. So when they're asking us to evaluate an integral, remember an integral means area under the curve if you have a curve, or it means you can do the fundamental theorem if you don't have a curve and all you have are equations. So we take the antiderivative of acceleration. The antiderivative of an acceleration function is a velocity function. and we evaluate that from 5 to 10. So doing the fundamental theorem means we plug in the upper bound, plug in the lower bound, and subtract. So these things were technically from our last unit. The average value was a good thing to look at, but this is all great practice. So V of 10, here's one thing I can do. If I go back to that graph page, this is my velocity function that's plugged in. I can add a table to this, and then I can see the values at 10 and at 5. So at 10, the value is 17.6715 minus the value at 5, which is 10.9064. All right, so 17.6715 minus 0.9064. So that is the change in velocity, which should be 6.765 feet per second, because it is velocity, so it shares velocity's units.